Welcome everyone back. Those of you that joined us sometime around 2 o'clock or earlier. Those of you that have signed on since then, I'd like to welcome you to this special webinar here, sponsored by Dynapar. And you're here for the webinar entitled Motion Feedback 101, Selecting the Right Feedback for Your Application by Knowing the Basics. So we will get things rolling here shortly. A couple of points prior to starting here. This webinar will be at the designworld.com website there afterwards. Also, everybody who is registered for the webinar will get a copy of this webinar via email as well. Also, keep in mind that we will have a Q&A at the end of this webinar. So if at any time during the this webinar you think of a question, please go ahead and feel free to type it into the questions box there, and we will do our best to get to as many of those questions as we possibly can. Also, if you're on Twitter and if you'd like to tweet about this webinar at all, we have the hashtag there for this webinar is hashtag DWWebinar. So you can also do that as well. So let's kind of get things started here. So my name is Miles Budimir. I'll be the moderator for this webinar today. I'm a senior motion control editor here with Design World magazine. And I'd like to present our presenter for today, and that is Mark Langille. And he is, his title is Servo Motion Feedback Vertical Manager with Dynapar Corporation. And give you a little bit about Mark's background here. So Mark is with Dynapar, obviously. He's worked in the encoder industry for 15 years, both on the manufacturing and commercial side of the business, with 7 years spent as a manufacturing engineer. He has a BS in Industrial Technology with an emphasis in manufacturing from Iowa State University. So he brings plenty of knowledge with him, and without any further wait here, I think I will just pass it on over to Mark and let him take it from here. Mark, so it's all yours.
Miles, thanks for that introduction, and thanks everybody for joining on. I'm looking forward to giving you guys some of the basics with regards to encoder selection going forward. I was going to take a quick impromptu poll for all the people who's rooting for the Blackhawks in the Stanley Cup Championship versus maybe the West Coast teams that they have yet to play. So if you're on the West Coast, you may get disavowed from the webinar if your intentions are not with the Blackhawks. I'm just kidding. Should just a little Chicago plug for Chicago. But at any rate, we're talking here today about rotary feedback. Just to kind of set the stage, you know, essentially rotary feedback encoders, resolvers act to digitize the motion, rotation of a shaft in some type of automation system or machine, such that the control aspect or the control piece of it, PLC or drive, can react in some way to drive, you know, additional automation into the system. So essentially, you know, we're looking at closed loop rotary feedback control schemes, and a variety of ways or reasons why you would want to close the loop. You may be controlling for speed. You could be controlling for velocity, which means you're controlling for speed and direction. Or you may be resolving position data. It really kind of depends on the application. And there are several different ways that you can close the loop. You can close the loop on shaft velocity or position. You could close the loop on motor torque, which would just involve monitoring motor current. Or you may have a secondary sensor that could monitor the load end in a machine and close the loop based on that. Or you may have a PID loop, which could nest any or all of these together depending upon which one was the most important variable. But essentially today we're going to be covering shaft position and velocity and how utilizing feedback in those scenarios can improve and create better performance in the system. So when we're picking the type of feedback, basically this is a litany, a laundry list of the type of things that if I'm working with a customer, I'll roll through and try to discern the type of resolution that's needed in the application, accuracy, maybe something along the lines of the velocity ripple or speed variation that is tolerated. We'll take a look at the uptime and reliability that they're looking to achieve. Cost, always an important factor. Also, we'll take a look at the mechanical constraints and IP ratings. This is just, kind of a signpost as to the type of things that we'll look at when we're taking a look at encoders and resolvers. And the presentation today compares and contrasts the different types of feedback and where maybe some of the strengths and limitations are with regards to the variety of different ways that you can create closed-loop rotary feedback. So the first compare and contrast different horses for different courses is encoders versus resolvers. So encoders versus resolvers. We'll start with resolvers. So what we're showing on the screen here today is a wound resolver. We call this the rotor, and this is the stator. You can think of the rotor as essentially an electromagnet, right? And that has an induced electromagnetism from the rotary transformer that's here in the stator onto the rotor, and there's an excitation frequency that goes in to that electromagnet. That magnetism is swept around the stator coils, and those stator coils are then basically transform the sine wave that's inputted into the excitation frequency into the sine and cosine wave as the windings on the resolver are sinusoidally wound. And you can look here on this diagram, and it shows that essentially these stator windings are 90 degrees out of phase to each other, and then that's what creates the analog signal, sine and cosine. And then those ratios of those voltages are what produce the angular position. And essentially, the resolver, a single-speed resolver, is a absolute device. So you know where you are within one revolution all the time. So just a little more detail on the inside of the resolver. In the construction of it, there are no electronics, right? It's essentially largely what you would consider to be the same components that are in motors, copper windings, laminations, aluminum and steel housings, and things like that. So there are times where, in applications where a resolver is a good fit because it's very robust. It can take high temperatures. 155 C rating is kind of commonplace, and there are versions that go up to 220. What's going to dictate which size resolver you might pick is based on really the shaft size that would interface with the resolver. So resolvers are kind of typically sized. We size resolvers from size 10, which equates to 1 inch, and then kind of working up there. So size 15 is a 1.5 inch, 2.1 is a 2.1 inch, going all the way up to 55, size 55, 5.5 inch. So they can fit a variety of size applications with a resolver, and you can see they're offered. The one that we're showing here is a frameless resolver, so it's 2 parts. But there's also a housed resolver, which is essentially, more conventional and would be interfaced with the shaft. You can also see fairly high accuracies with the resolver, even all the way up into the 6 arc minute range are not uncommon. So it can be a good fit for many applications. As I said, because there's no electronics on there, it provides a high level of robustness. Temperature extremes, they're available in versions that can take radiation. They're more or less immune to contamination. And then shock and vibration are largely not a concern. The output is analog. And so from an interpolation perspective, you can think of the resolution as infinite. And you often see them in tough applications like aerospace, servo, and CNC. The one limitation or thing to look out for is that there are electronics that have to go somewhere. Usually they'd be put back in the PLC or the drive that the resolver might be connected to. And what that requires is that, as I said earlier, the excitation frequency and at a specific voltage needs to be sent to the resolver, and then that needs to be converted via an A to D converter, usually to be read into some type of system. This is usually done either via an FPGA or some other type of dedicated off-the-shelf chip set that will both control the excitation frequency to the resolver and then do the reading of it on the way back for the sending the signals into the control device. The other aspect and kind of skill required for integration of a resolver is good control over the total indicator runout in the case of a frameless resolver where the rotor is mounted. The resolver relies on control of that air gap, and so just in the mechanics and thinking about how to integrate a resolver if you're using a frameless resolver, it's important to control that total indicator runout of the shaft. So by contrast, when we take a look at encoders, essentially the digitizing of the shaft rotation is done on board on the encoder. And so what we're showing here in this diagram is just a simplistic view of the A channel and a B channel, and you can see that those instead of having some type of sine or cosine wave, that those structures are square waved off and read digitally into the control. And then that's used to discern speed and position and maybe a reference from an index signal. So basically the key element there is the encoder takes care of the digitizing versus a resolver, which requires secondary device to interface with the resolver. So when I think about encoders, there's a wide variety of devices that are available. They can be made more robust by adding potting to the electronics. Many utilize ASICs, which basically bring together many of the components that might have been discrete components in the past. So that helps make them more robust. There's lots of options when it comes to encoders: optical versus magnetic, incremental versus absolute, a variety of IP ratings, and mounting styles. And we'll go into those later on in the discussion. The golf bag analogy is that you could go out and play a round of golf and maybe take one or two clubs, but inevitably it's nice to have a full set of clubs to hit different shots. And it's much the same way with encoders. There's a right device, and kind of understanding what shot you're trying to make and selecting the right device can make a difference for those types of applications. So we'll come up on our first poll question here. In rugged environments, where is it best? What device is best to specify? Resolvers, magnetic encoders, optical encoders, or depends on application? Miles, I don't know, will there be buttons that pop up on this, or just something to consider?
I think there should be. There should be, I think. But
okay.
If not, if that doesn't happen here, then I think we could just go with it being a rhetorical type question, I guess.
Sure. I can just talk to it. In general, I would 9 times out of 10 give the tip of the cap to resolvers as being best for rugged environments. There are magnetic encoders and optical encoders that I've seen that live in very tough environments as well. But when you talk about kind of the worst applications, a lot of times resolver is a key choice, especially when you're talking about heat in high temperature applications. If your temperatures are down below, your operating temperatures are down below into the 130s and below, it's definitely a realm where you can start to consider encoders as an alternative. If you're up above that 130 range, you're really into resolver territory. Okay, so we'll move on to the next slide. So the next compare and contrast here is optical versus magnetic, and I sort of view this as a taste great and less filling argument. We can go back and forth about different aspects about which one might be better for a particular application. Again, each type or each category has some nuances about it. And really these days there's some opticals that do a lot of things that magnetics only were able to do, and vice versa. But if we just talk about optical encoders for a second, essentially from a basics perspective, you have a disk that kind of rides between a sensor and an LED light source. And that disk breaks up the light path. If you almost think about the LED as like a laser shining through the disk, and whether the light is able to transmit through and activate the photodiodes on the back side through the mask, or whether it's blocked, is what creates that square wave signal that we saw on a slide before. And as the speed of rotation increases, the duration that pulse that the photodiode sees the LED light gets smaller and smaller, and the width of that incremental output pulse gets more and more narrow. So that's how essentially that's how the signal, the rotation is digitized. So there's also commonly a mask that's employed over top of photodiodes to help basically make the signals more crisp by blocking kind of stray light. And so there's a type of optical encoder construction that will employ a mask, and then kind of newer age encoders will use a phased array ASIC on board, which doesn't necessarily require a mask, but has the photodiodes down at the root level of the silicon arranged in basically much the same vein-like pattern as the disk. This helps to compensate for misalignment. It can potentially make the encoder more robust by eliminating a bunch of other components that would be on the board to create the digital signal. A phased array like that will also allow for a larger air gap, and from a pricing perspective, they can offer some advantages as well. So optical encoders, from an application perspective, we see in a number of different applications, really a wide swath from medical, semiconductor, elevators, oil and gas, aerospace, and heavy-duty vehicles. So they really cover a wide variety and can be used in lots of different applications. The trade-offs with an optical encoder, the things that you do get, 10,000 up to 10,000 PPR direct read, and there's a little bit of a nuance there for a direct read encoder, which means the actual line count that's on the disk, versus using some electronics post-processing to increase that resolution. But essentially, 10,000 PPR is a very high PPR device in a direct read. And then when you get into absolutes, we'll talk about encoders that have millions of counts per rev. And we'll talk about that more later. An optical encoder offers some advantages in terms of ease of installation, because they often will employ bearings and tether mounts and rigid mounts that makes ease of installation very easy. They tend to be very immune to EMI as long as the right considerations have been taken in for cabling. Very highly shock resistant, and they come in at a good price point. But as the photo up on the right-hand side shows, ingress protection is a consideration with an optical encoder. And the photo in the upper right just kind of meant to exemplify that optical encoders can be used in dusty, dirty, wet environments as well. With optical encoders, utilize bearings and have LEDs. I would say by and large, most encoders are designed, given proper application, to have, let's say, a 20-year life. But it's very important about how it's applied, and so that gets into the nuances of knowing your application and then knowing some of these terms and specifications to selecting the right one. So moving on to compare and contrast a little bit, magnetic encoders are normally comprised of a drum or a wheel that has alternating magnetic poles, a sensor or readout electronics, and it's basically the changing of the north and south pole in front of that sensor that create the pulses. we've seen over time that magnetic encoders are real applicable in mill applications, cranes, extruders, and washdown, heavy-duty washdown environments. You'll see a lot of them as a highly robust device. And like I said, with today's electronics, you're seeing wider air gaps, and essentially we view the wider the air gap, the better, because it just allows for more variation elsewhere. If your sensor and magnetic wheel have a high amount of allow for a high amount of tolerance between the two. Magnetic encoders tend to be the most rugged and the most reliable for heavy-duty type applications. A couple, kind of going one level down, we've got a couple different type of magnetic technologies. We've got variable reluctance technology, which is a little bit, I'll call it somewhat older school. It has some limitations in terms of the PPR that it allows for, but it's a relatively simple pickup and toothed wheel approach, good for up to 240 PPR. We have magnetoresistive, or AMR sensor, and those register changes in the resistance value as the drum rotates in front of it. They offer basically almost like optical accuracy and good accuracy and resolution. They don't necessarily allow for the largest air gap, and there's some analog signal to digital signal processing with those as well that's required. With Hall effect sensors, which there's a lot of interest in these days, and we in Dynapower often employs, it's a solid state detector, and it has an integrated processor on the chip, and so that enables the signals to be processed right down on that root level. They're again kind of reducing the number of components and improving the overall reliability. Compact and economical, and multiple detectors over the span of the sensor, lower the noise and increase levels of sensitivity. So this is an exciting technology to have employed. So for magnetic encoders, they're tough. They can basically be unaffected by contamination. They can delve into those realms of 120, 130 degrees. They've got good shock and vibration and stable performance if you employ a bearingless style of magnetic tack. No worries about bearings. And it may have on the lower end, and this is a little bit of tastes great and less filling, but on the kind of everyday industrial type of encoder, may offer up to 5,000 PPR in resolution, and can be affected by magnetic fields, but I would want to clarify that magnetic encoders typically could be used with electromagnetic breaks all the time. The type of magnetic field that may be of concern could be like an MRI machine, where you're up into the several Gauss of magnetism, and magnetic encoders for that reason may not be the best choice. So poll question number 2, which type of rotary feedback typically can provide the highest accuracy, resolver, optical encoder, or magnetic encoder? Or D, depends more on the application and the environment. So for my purposes, I would tend to give the nod to the optical encoder. Some of the highest resolution direct read encoders that I've ever run across are all the way up into the 36-bit direct read resolution for maybe even space-rated applications. So highest resolution, highest accuracy possible, I'd still tip of the cap to optical encoders. But with resolvers, quite commonly or easily getting into the 6 arc minute, and magnetic encoders with investments in new technology coming out of that, it really does depend on environment and which one you might choose. Knowing that they all have solutions, each of the technologies have capability up into what I would call the everyman's need for resolution and accuracy. So a little bit now on incremental encoder versus absolute. As we talked about a little bit earlier, incremental encoders typically have a A and a B channel, and they could also have the complements for noise immunity, and then an index. You're using that channel output to measure speed and velocity. You could use the index channel to track a position location from home, and then that pulse stream is being sent to a PLC or drive to convert the info. So basically, you know where you are only once per revolution with a incremental encoder. The quadrature encoder can be utilized to basically increase the resolution by looking at every edge in relationship to every other edge. And that's how you can use a quadrature encoder to get essentially additional resolution for position indication. We see quadrature encoders used quite frequently in web applications, packaging equipment, and motor and drive applications where a tight speed loop is required. With an incremental encoder, trade-offs and benefits. With interpolation, you can see up to 32,000 7068 PPR is not uncommon these days with interpolation factors. They're relatively simple to integrate and easy to maintain. And really the slide here is to talk about the selection. There's an encoder type, and you should work with an encoder manufacturer that has a wide variety of devices. With an incremental encoder, often a machine will need to be rehomed at startup, and from a cabling perspective, it may require a cable with A, B, and Z in full complements, power and ground, 8 or even 10 conductors for the cable. So cabling requirements can add to cost, and it's something to take into consideration. But I think when you're looking strongly at an incremental encoder, you can rest assured that there's a device out there that will suit your needs. In contrast, with an absolute encoder, the device, the encoder, is putting out a digital word that corresponds to the absolute position. Each ring in that code disk represents kind of a bit in the overall word. Standard resolutions for absolute encoders go up to 4096 PPR. They kind of start right there at 4096 at the base resolution, and they can go as high as 22 bits for the single turns, as equates to in incremental talk in terms of PPR. Absolute encoders also employ a multi-turn capability where the encoder itself will keep track of turns, the number of turn counts over the whole span, up to, in many cases, 4,096 turns. And absolute encoders often support bus and Ethernet communication protocols, which there again can help, in contrast to incremental, can help reduce wire count and reduce cabling burden. For a motor application, you might turn towards a serial encoder rather than a bus style encoder, because a serial encoder provides better determinism for the position. We see absolute encoders quite often used in high accuracy applications, medical, aerospace, semiconductor. There's some advantages from a system tuning perspective where you have multiple axes, and you can use an absolute encoder to dynamically tune where it may be limited with an incremental. And then again, serial versions are best for ultra low speed because you have high resolution from an absolute encoder, ultra low speed PID loop control. So some of the trade-offs, absolute versus incremental. No need to rehome upon startup. So faster startup time means more processing time potentially for your machine and its application. Some level of greater accuracy and resolution, bus compatibility, and the ability to, if you're connected up to a bus style encoder, you could view that as diagnostic capability where you can go out on the bus potentially and pull the encoder to make sure that it's working and connected to the system. There's a little bit of a cost premium in some cases with an absolute encoder, and it may often require an EDS file, electronic data sheet file, to do installation onto the bus, or a hardware software master for it to connect properly with the drive electronics in some cases that you may be using. So that's some of the trade-offs, incremental versus absolute. So a polling question, which device allows you to sense the absolute shaft position in within one rotation? So optical incremental with index, optical absolute, magnetic, resolver, or all of the above? Everybody out there remember from grade school, do you always pick C or E, all of the above? In this case, the most correct answers are optical absolute and D, resolver. Those give you true absolute position within one revolution. You could give a little bit of a tip of the cap to optical incremental with index, in that if your machine's rotation is only within one rotation, you may always cross that index pulse and may be able to discern absolutely where you are within one rotation. But really, optical absolute or optical magnetic or resolver are the main devices that will allow you to have single turn absolute feedback. And then most of the time, unless you're employing multiple devices, an optical absolute or magnetic absolute would be ones that provide absolute multi-turn capability. So now that we've gone through what I consider to be the major types, sensing engines, resolver, magnetic, optical, and then optical incremental and optical absolute, we're going to talk a little bit about the mechanics. Once we've gotten the resolution and accuracy necessary, and we have a sensing engine that we think can stand up to the application situation, then we start to take a look at the mounting types necessary. So we talk a little bit about shafted encoders. It's kind of the most commonplace and really where much of the rotary feedback industry kind of started, with shafted encoders. Oftentimes they're coupled on a non-bearing side, non-load bearing side in a motor shaft, or they could be, as this one is, connected into a gearbox that's driven by a motor, or even a measuring wheel that runs along in a web handling or on a conveyor application. They can be very robust, and as we talked about, they offer a great variety of options. With shafted encoders, when you're making that connection, maybe via a belt, and in this case, a little bit difficult to see, but you have an encoder down here tied to this belt that's on this gear reduction system, and that's essentially sensing angle or position as this gearbox is rotated in a lumber manufacturing application. So we're using the belt in this case. Wheels are perfectly acceptable, or a flexible coupler that allows you to stay within the rating, both axially and radially of the bearings that are in the encoder, and those are usually listed on that specification is usually listed on the data sheet. You just want to be mindful that the dynamic loads don't exceed the encoder's bearings rating. So when we're looking at shafted encoders, that's kind of one of the key elements that we look for. On the flip side, you can also employ a hollow shaft encoder. This just mounts directly to the shaft, uses some type of pressure fit to clamp onto the shaft. It reduces the amount, or basically provides automatic alignment. No couplers are needed. Fairly rapid to install. You don't want to take the tether mount for granted. A lot of times we see crazy, the tether is kind of the spring or a rod style tether that attaches and is the anti-rotation device for the encoder. And it shouldn't be taken for granted, which you would want to follow normal considerations for having the tether kind of square to the mounting face of the motor or the mounting surface, and not having it bent and torqued or having a force imparted on it. Hollow shaft encoders are real common, like this, HS35R, are real common in AC induction motor feedback, kind of a de facto standard for the industry. You also have bearingless encoders. Both both magnetic and optical. What's shown here is what I'll call the most rudimentary device that requires the most amount of protection, which is an optical bearingless or modular style encoder. You have the sensor unit, and then you have the disc that's mounted to the motor shaft. No bearing, so it obviously offers some advantages from a maintenance perspective. It's light. The sensing principle is non-contact. Here again, close attention, especially with an optical modular encoder, should be paid to shaft runout and end play under the mechanically loaded conditions, so that you don't violate the air gap or offset that's required to be maintained between the sensor, LED, and disc, like we saw from the initial slide. So we've covered kind of the major styles of mounting and major device types. We get into one of the last sections here with regards to IP rating. So we commonly use the IEC 60529 standard. It's a two-digit system. The first digit talks about the solid and flyings and dust particles. The second digit is the type liquids and droplets to high pressure. Careful to look closely at IP ratings, durations of time, depth, and so on and so forth. There's some trade-offs with regards to seals. You could specify let's say in this case, the encoder here is an IP69K rated for high pressure steam washdown. But adding extra sealing protection can add extra heat to the encoders running. And so you want to balance that out with probably, in many of these specifications, less is more. And you want to pick one that fits the right running speed versus the IP protection that you need. So this is a look at the chart for IP protection, and it gets into the code, the IP code 6 in this case being the designation for the dust type, whether it's dust protected and to what size, and then just as important is the liquid rating on the back side or on the lower part of the number, and that'll tell you what type of ingress protection with regards to liquids the device has. And you want to match that with your particular application. So running through the sensing engine, and different device types, the mounting styles, and how that may be interconnected to your system, and then how that is protected from the outside world. So, sort of as a synopsis, you want to start with the necessary. I always say that an encoder resolvers are electromechanical devices. So you start with the electro piece of it, and you get into accuracy, resolution. Want to be looking at phase and symmetry, and then the output side of that, the electrical interface, and then carefully consider the environmental conditions with regards to temperature, IP rating, shock, and overall reliability. And then, of course, no discussion is complete without a total cost of ownership. What can you budgetarily afford for your particular application? So, in summary, we've got resolvers kind of being one of the for the harshest of applications. An optical encoder provides good resolution and fits many needs. And you have the magnetic encoders, which offer that next level of robustness and can be the best of both worlds. Don't necessarily choose a high IP rating just to compensate for the wrong choice of feedback type. And while no one device can do it all, kind of going through carefully the different specifications that we've covered here today should allow you to pick the right device. So I hope that our discussion has been useful and informative, and I look forward to questions here on the backside. And again, I'd like to thank everybody for joining me for this 40 minutes.
Okay, well, thanks a lot, Mark. So we've still got plenty of time here for questions. Obviously, we're in that part of the webinar now, in the Q&A part. So there's already some questions coming in, and if you have any that you can think of right now that you'd like to ask Mark, feel free to do so. Should be like a questions tab there on your screen as part of the webinar software. which you can just enter the question in there. And like I said, we'll try to get to as many of the questions as we can. I guess let's begin with some questions here, some of the ones that have come in. Okay, so this goes back to what you were talking about. You're talking about environmental conditions, and this one, this person has a question about, could you give us a practical example of what you would mean by a rugged environment, basically?
Okay, so a rugged environment. When we talk about rugged environments, I normally think of one of our core applications in pulp, paper, and steel, and especially in a paper mill application. Oftentimes, magnetic encoders would be used because they really are sealed and potted to prevent or to be immune to ingress of material. A paper mill can be a very difficult application because it does, especially on the wet end of a paper mill, because it does have both liquid and solid material that can be carried in via the slurry on the pulp side, and so that would be a real rugged application. Also in some aerospace type applications where temperature could be a factor, and maybe even having to have the device embedded in oil. Maybe the actuator may run in the bath of oil that may be lubricating or hydraulic fluid. In many cases. So those are two fairly ruggedized applications: pulp, paper, and then in some aerospace applications.
Okay. So it sounds like it sounds a bit like one of your last slides there, where you kind of tried summarizing it by saying, know what your application is. So know probably what types of temperatures there are, if there's going to be liquid, if there's going to be, dirt and dust, and if there's going to be, any of those, pressure even, I guess, too, force or shock or anything like that, right? Those are all things which I guess, all depending on what type of application you're actually dealing with, those are things that you would need to know, as you kind of pointed out there, I think.
Yeah, exactly. Yeah, another one which has come up more and more as further automation in the food industry has come about, and requiring high pressure steam washdown, and that's where you get into specifying something that's IP69K rated, at kind of the top end of ruggedness from the IP rating perspective. Okay.
All right. So here's another question now about resolution. So this question is, what is best for high resolution applications, and what is the highest resolution out there without getting too esoteric, I guess?
Right. So a high resolution application could be quite often involving CNC applications, so like CNC machine tools, or quite often anything that requires in the servo motor application. A lot of times you will see the kind of stock resolution necessary for high accuracy, speed, and or position control be in the realm of, kind of start at 2048 realm. We see that specified, quite often across the board at 2048 for high speed or high accuracy servo applications starting at 2048, and then ranging up. So I think that would be the 11 bits. So then 12 bits would be double that, 4096, and then 13 bits being 8192. Right now, in the upper echelon of absolutes, I see anything above 19 bits as being pretty superfluous in an industrial encoder. There's a little bit of a nod to highly specialized devices that can go above that, but in the industrial encoder realm for standard motion control, I would put that variance probably 13 to 17 with the upper echelon at 19 bits if there's not too big of a cost penalty.
Okay.
Okay.
All right. Yeah, that sounds good. Okay. Okay. Go on to a different question here. This is asking, can you explain what you meant by dynamic load in regards to the shaft incremental encoders?
Okay. So what I was referring to is you have a encoder that's sort of maybe installed steady state, or when the encoder is installed on a particular shaft and it's not running dynamically, and you don't have a load in the machine or on the machine, whatever that machine is, whether it's a gantry moving back and forth or a web application with paper or maybe steel moving through different drive rollers and things like that. There are cases where basically once the load is applied, once there's material in the machine, there could be a shaft whip depending upon speed involved. There could be axial play that comes into effect, and so you want to be able to quantify what the behavior of the, let's call it the spindle, will be when it's mechanically loaded, when it's dynamically loaded, such that you won't violate whatever the axial and radial play requirements are, and really, axial and radial play from an encoder perspective, whether you're talking about magnetic, whether you're talking about absolute, or whether you're talking about incremental, all of them, all encoders should have and should look for the axial and radial play allowance, either in the tether or in the system if it's a two-part sort of modular device.
Okay. Sounds good. Sure.
Okay.
Take another question here. So this one deals with outputs. The question is there a preferred encoder output, for instance, line driver or discrete or pull-up, that is most popular, or is the output type driven more by the controller hardware?
It's often driven by the controller hardware. In this day and age, and a lot of what I deal with, you quite often see if the encoder is connected into some type of motor drive, and you're doing closed loop speed or position control for a motor, you'll see that be a line driver output, and that's normally because with line driver outputs and longer cable lengths, you will see a line driver and differential signals, which is the A and the A naught, which is essentially brought into an opto isolator and then refined into a single signal inside the controller. Better noise immunity, right? So they'll use a line driver. But I'll just say this: if you're under 25 feet and you're going into, let's say, just a PLC, a lot of times a open collector with pull-ups is perfectly suitable. You don't need line driver and full differential, 10 conductor cables and super. You always want to pay attention to shielding in either case, but open collectors are still perfectly good, and you end up, in fact, you end up putting less heat into the encoder. Less heat into the encoder, can help extend the life. So open collector with pull-ups is a good choice when the cable run is a little shorter, and you want to keep some heat and maybe get closer to that 20-year design intent life of your device.
Okay, and that was, you said, like under 25 feet or so, right? Is that what you said?
Typically under 25 feet. Yeah.
Okay. Let's take another question.
Great. That was a good questions.
Yeah. These all been pretty good so far. All right. So here's another one. This one asks, what are the considerations when trading between resolvers versus optical encoders if ruggedness is not a primary criteria? So, for instance, in a controlled environment such as a laboratory or a R&D type setting, for instance.
Yeah, in an R&D type setting, then I would look to probably, it becomes more about what you're attaching to, right? And if you're I'll say this, into a PLC, right, in a laboratory environment, or maybe let's say into some type of counter card, right? depending on if you're like, let's say you're using, National Instruments type of equipment, or you're using PLC. A lot of times, quadrature encoder input or even absolute encoder input will be easily implemented. There may be a off-the-shelf code, right, that you can use, or let's say it's a DIY type project where you've got a processor, some type of PIC microchip, and you're deciding, should I use resolver or should I use encoder for just sort of a test bed setup. An incremental encoder is so ubiquitous, and so there's so much off-the-shelf code that makes it easy to do incremental encoder that I would only pick the resolver in that case. Maybe if there was some reason from an IP ingress protection perspective that you wanted to have the resolver, or if you were looking for potentially once you're out of the lab, you were looking for if you're looking for in the lab but you wanted absolute, and you wanted because the resolver is absolute. But if you can stand homing the system past an index mark or hitting a limit switch to kind of gain position, incremental encoders is a really cost-effective way to get highly accurate feedback.
Okay. All right, sounds good. So another question. This one's kind of a, I guess, kind of a overview question, I guess, or maybe more practical, I guess, too. But question is, should I specify an encoder with the highest resolution that fits within my budget, let's say?
Okay.
So I guess getting maybe something along the lines of getting more bang for your buck or something like that.
Right. Yeah. I mean, higher resolution, right? Bigger is better. Sounds like a good principle, right? If it doesn't cost, if the difference between 2048 and 10,000 count is no difference, then I'll pick the 10,000 count. One thing to consider carefully with regards to in an application where you've got a long cable run and you've got a lot of resolution is essentially you can think about that cable as the encoder signal is being transmitted through it as having to constantly charge and then discharge and then charge and discharge. And number one, again, it builds up heat in your line driver based on the number of charges and discharges. And so it can be taxing on a system when you have higher resolution because your number of charges and discharges increases. And driving through that cable, you can think of it almost like a water pipe, right, with kind of holes in it. As that charges and discharges, there can be a certain amount of distortion that comes onto the signal. So I like to look at it and try to first find out if what the minimum resolution is that might be required, and then maybe go one step up, but not go bigger is better for that reason, just to kind of reduce signal distortion and keep heat out of the system, improve the overall longevity of a system and of the encoder.
Okay.
All
right.
Good question.
Okay, good. Maybe there's a kind of I guess a technical question that I had as I was kind of listening to, but in the section where you were talking about the magnetic encoders, you mentioned that they were typically lower resolution than the optical ones, and I was wondering, is that kind of a property of the technologies themselves, or is it just or is that kind of changing as kind of time moves on, or
I would definitely say that. Yeah, I mean, to me, and I tried to highlight it a little bit, that to some extent, I feel like the times are a-changing with that, because as more and more devices are incorporating Hall effect sensor arrays, they're able to jockey higher resolution and even in some cases higher accuracies, right? And there's a little bit of a distinction between resolution and accuracy there. But certainly the magnetic devices are getting into, and there's more and more overlap. There's more and more overlap in my mind between each. There's optical encoders that are getting pushed into more and more rugged environments, and then vice versa. There's magnetic encoders that are getting better and better in terms of accuracy. So I would kind of I would agree in concert with you that in the past it's been a function of the raw sensing technology, but with some of the Moore's law taking to effect and higher computing capability being able to be embedded down into some of these ASICs, higher resolution is becoming more and more available in both realms. Okay.
Okay, good. Yeah, and that I mean that kind of makes sense, I guess, too. If you look at where technology has been and where it's heading, and that seems to be to perfectly kind of line up with that trend too, I guess. So.
Yeah. Yeah, absolutely. And there might be, I don't know, we may have a webinar coming forward just to forecast on some of the higher tech aspects of we talked a little bit about line driver, and maybe we could get into more detail. This was meant as a 101 overview, but like to do maybe a coming attraction, another webinar coming on some of the higher tech stuff.
Okay, good. Coming soon.
Okay. Coming soon.
Something like that. All right. Well, let's see if
Exactly.
we can get in one more question here, since we are coming up to 3 o'clock here. But see how we can do with this one. So this one says using quadrature input and ABZ signals, can I expect this 20,000 PPR resolution from a 5,000 PPR encoder?
Yes, you can effectively have 20,000 in the ×4 configuration with a 5,000 PPR encoder. You could expect 20,000 edges if you're reading in quadrature to resolve position. So between those edges, you may not know explicitly where you are, but you could employ 20,000 edges by which to discern position. So that is true.
Okay.
Okay.
All right. Good. Well, I think we're probably.
Yeah, but I wouldn't. But I wouldn't confuse that. I wouldn't necessarily confuse that with one thing that's done is some people will talk about PPR, pulses per revolution, which is the base resolution, and I wouldn't confuse that with in quadrature. When you're specifying and talking about encoders, you want to be try to use the right jargon or terminology, which is pulses per revolution, which equates to the base the base resolution that's on the disk versus in quadrature and multiplying it ×2 or ×4 tends to confuse things. So
okay, good point.
Great.
Okay, it looks like we're coming up to the 3 o'clock hour here, so it looks like we're gonna have to probably cut things off here. But as you saw on the slide just prior to the one that you're seeing now, there's contact info for Mark and also for me as well. So if we did not get to all of the questions here, or even if you have some kind of follow-up for either me or Mark, preferably Mark, because he's the expert here, feel free to certainly email him or call him, and I'm sure he will help you out. So once again, I want to thank Mark for your time today and for your knowledge, and thank all of our registrants and all you folks that signed on here today to be with us for this webinar. A couple of final points here. This webinar will be up at designworldonline.com, so you can go there and get the webinar afterwards. And also, if you've registered for the webinar, such as everyone who's here did, you will get a copy of it in your email as well. You can still tweet about the webinar at that hashtag DWWebinar. You can connect with Design World through various ways. We are on all the social media platforms, including Facebook and LinkedIn and Google+, and Twitter, of course, and probably any others that will be coming up soon, I'm sure. And you can also continue this discussion over at engineeringexchange.com. So that's a little from our side, and obviously you have Mark's contact information and Dynapar's contact information there as well. So you can certainly reach out to them if you have any more questions. So once again, I can thank everyone and wish you a good rest of the day and rest of the week.
Miles, thanks a lot, and thank everybody again for joining. Appreciate it.
Okay. All right. Take care, everyone.
Okay. Bye-bye.
Bye-bye.